Hey, what's going on, folks? It's Mike here, and welcome to the Software Design Series. In today's lesson, we're going to do an introduction to the strategy pattern, and then in a follow-on video, we'll actually code it up, and you'll get to see how to write it in modern C++. So with that said, let's go ahead and talk about the strategy. Now, the strategy pattern itself isn't a complicated pattern, but what's really useful about the strategy pattern is knowing when to apply it. So that's what we're going to focus on in this video. So anyways, let's go ahead and dive in here. So let's just go ahead and start off with what is the strategy pattern here. So just to read it off here, the strategy pattern, which also goes by another name you might have heard called the policy pattern, is a behavioral software design pattern. So behavioral patterns, again, have to do with, well, how do we do something algorithmically and usually making some sort of choice. So we're going to emphasize that in this video. So the basic idea is that this software design pattern that enables selecting an algorithm at runtime. Because again, our programs might want to be able to do things in a more efficient way. So we need to be able to choose while our program's running, maybe this version of a sorting algorithm versus that version of a sorting algorithm. So hang on to that thought and we'll go ahead and look at that in this video. So instead of implementing a single algorithm directly in our code, the code receives runtime instructions as to which in a family of algorithms to use. So again, that's going to be an important point here, choosing from a family of related algorithms that can do the same job, but the behavior is going to be a little bit different in how that task is achieved, or I should say how we achieve that behavior is going to be different. So with that said, let's just go ahead and think about this from a programming standpoint. Now, if you watched my previous video on the visitor, so make sure you check the description for a link to the rest of the videos in this playlist, you saw that we talked about this idea of, well, programming paradigms and had a general understanding of where the visitor comes into place. So we're going to do the same thing here with the strategy pattern and talk about what does it mean in general to change algorithmic behavior? What are our tools? Well, our tools are things like if, else if statements, switches, maybe even go-to statements that you can use to basically jump around and branch and do different things in your code. So again, that's one way that you can change the behavior. Now, what goes in those different if blocks is, again, how you're achieving some sort of task. So let's go ahead and take a look at this. And the example that I want to take a look at here, if I draw your attention right above me, is an example from the standard C++ library. This is actually a sort algorithm here. So it's from one of the versions of the standard here. And I want you to see that I've highlighted here this threshold variable, first in orange, and then you can see the yellow highlights to see where it's applied. Now, what this threshold is basically an enum, so some constant value, set to 16. And we have this branch here that's saying, well, if some last minus first is greater than this threshold, do this set of algorithms here, this insertion sort and then an unguarded insertion sort. Otherwise, do this version of an insertion sort. So it's kind of interesting that somebody's identified some sort of threshold, maybe empirically or by whatever means for this data type, that maybe sorting is better if we do this first, if we're greater than some threshold versus if we're less than some threshold. So that's an example of choosing different behaviors. Now, what this unguarded sort is, an insertion sort, we don't really have to worry about it, but there are different types of sorts. You can look up intro sort and some of these different things which use an insertion sort on a smaller collection versus just defaulting to, say, quick sort or merge sort, right? So again, there's different reasons to use different algorithms. That's why we study all sorts of different sorts. They're different. They're good use cases for understanding complexity and system behavior if we measure. So getting to the point here on changing algorithmic behavior, when our program is running, we might have a container or a vector that's, well, sometimes it might be greater than 16 elements and sometimes it's 16 or less elements. So we want to be able to change behavior so we can sort our data as fast as possible for the user. So again, if the workloads change, that's a reason you might want to change behavior. Or perhaps there's some other state in your application that's changed. Maybe let's think about an example in a game, for instance, where you want to change how the game AI responds to the player, maybe by difficulty level or how well the performance of the player is doing in that game to make it more or less challenging for them. And perhaps your system just has more or less system resources available. So for instance, if your memory is low, maybe you want to do some algorithm that doesn't allocate space versus some other algorithm that does allocate a lot of memory so you can get more performance. So again, there might be different reasons to pick and choose these algorithms, especially on really dynamic systems or distributed systems where resources are more important. And you might also just have some error state that's entered, so you might want to change behavior and start logging things. And that's where, again, you can use the strategy pattern that we're going to learn about today. So here's an example, again, motivating where to understand where we're going to want to use this strategy pattern, this ability to change behaviors. I mean, if we look here to the left here, this is a way to change behaviors. I've got if, else if, else if, else if, and my conditions here. And I want you to just pause the video so you can hit spacebar or press the pause button here really quick and just think about this for a little bit. I mean, is this reasonable code that I've written here? And if you paused and thought about it, your answer might be yes. I mean, and that's fine. I mean, again, understanding design patterns is about being able to understand the trade-offs and what's important here. But what's interesting here is if I have these nice sorts packed into different functions here, so tim sort, merge sort, intro sort, quick sort, whatever we want to add here, this isn't too bad of code maybe for you, okay? Now, of course, if I ask the question, how maintainable is this, and if it's reasonable, again, your answer might be that this is fine. You don't see anything wrong here. Now, of course, I can exaggerate this example, which in some cases I have seen real code like this, like in a compiler, for instance, but maybe in that domain it's okay. Again, we have to think. But again, you can ask yourself, is this reasonable code that we want to run here based off of some condition, do this algorithm, based on some other condition, do this algorithm. So think about this a little bit and think about how maybe over the years this might be a little bit tricky for us to maintain, which is certainly possible, right? As we exchange code between different programmers on a project that's long-lived, maybe folks will see this and say, I don't want to touch that code. So again, you have to kind of consider the maintenance of this code and what time frame that's going to be, and if it's something that's reasonable in this domain that you're programming in, which for a compiler programmer, maybe you have lots of code like this, but for a graphics programmer or a game programmer, maybe this looks weird. So let me move out of the way for a moment here. Again, I've been nice and put everything on one line here, but what if I'm not so nice? What if I actually expand out those algorithms here? Okay, so you can actually see some code here. And in some cases, this code might be longer or shorter or whatever, but here's some example sorts I've just pasted in here. And I will say here, this is a little bit trickier code. And maybe this type of code too, where I just have the algorithm and I haven't wrapped things nicely in functions, maybe it's tempting to start accessing global state and do some other naughty things like that that make our programs harder to maintain and test. So I'd argue that this code generally is not what we want to find ourselves writing. Okay, that can be very tricky. So again, let's ask ChatGPT or ask me actually. I'm a human. I've thought about these things. But this is probably a better way to write our code, wrapping everything in functions here. But the advantage that we get here by putting everything in a little function here and seeing our conditions is we can recognize this pattern where strategy is useful. So with that said, let's go ahead and take a look at this code again. So same code as we had before, some conditional, some behavior that we want to do, some conditional, and then some function to do the behavior that we want. And now the question I'm going to ask is, how testable is this code? Well, again, if I've got everything wrapped neatly into these functions, it might be reasonable to have a few unit tests for each of these functions, and that's fine. Again, if I go back to this, that's not so nice. So again, I'd say this code is very hard to test if we end up writing stuff like here. Even if I go back, this can be a little bit tricky, because am I writing one test for these threshold values, just arbitrary versions of insertion sort? Does my insertion sort work if I test it or have a unit test that happens to be more than 16 items? Maybe I get lucky, but what if I end up writing tim sort and I end up testing it on 15 and it doesn't work there? For whatever reason here, again, this could be kind of hard code to test here. I really have to think about how we're testing these functions here. So again, and what we're measuring, whether that's the performance of this actual function or this function within something that branches a lot with these different statements, is something that we do have to consider. So what I'm trying to get at here is we can notice a few things about this code, and maybe there's some ways to use some other programming tools to, well, improve this code here. So let's look at a few observations here that I've got. And what I'm noticing is common, and again, just to remind you of the definition of the strategy pattern, which we'll see here, is that I have a conditional, and then I have some family of related functions here. Okay, so here is the conditionals here, where I'm trying to change behavior, right? I have some if conditional. Now, an if statement really is for selecting, right, based off of condition, but I do want to change the behavior. Again, whether this is a sort, or maybe something else interesting in an application, you can think about your domain. But I am changing the behavior at runtime based off of some given input. And you could also do this at compile time, by the way. We're going to focus on runtime, but again, if you're really into doing stuff with templates and generic programming, you can of course do this. So with that in mind here, and this idea here with, okay, here we're changing the behavior. Okay, I recognize that. And now I see a bunch of related algorithms here. So I see different sorts. So again, that's a clue here that strategy pattern is going to be useful. And then we can also think about, and this is going to be leading into the implementation of strategy pattern, how do we group related things together? What's one programming tool that we could use for that? So give you a moment to think about that. And if you started thinking about this, well, let's figure out how we have a tool to do this. And the tool that we want to choose, the programming tool, should hopefully make our program a little bit more flexible in how we choose algorithms. And hopefully we can extend that as well easily. And we want to be able to manage things like the complexity of our code and have testable code. Generally speaking, these are the criteria that we'll want. So let's talk about first maintaining the flexibility to choose an algorithm and using that tool called inheritance. Okay, so maybe you thought about this mechanism here. Here is the classic example, a chart from, that you've probably seen in textbooks or variations of this, where you have a base class here, like a shape, and then a bunch of other shapes under it that are derived from this base class here. And that again forms triangle is a shape here. So again, just a brief inheritance reminder. Here's your base class, your derived class, and anything that is of a type shape, I can, instantiate a triangle or right triangle from, etc. here. So inheritance is a great tool that we can use here for us. So let's kind of shift this problem into sorts, because that's what we've been looking at. And let's say we create some interface here called iSorts, and then we can have insertion sort, bubble sort, quick sort, Tim sort, intro sort, etc. Any sort that you've learned about can be part of this interface here. Okay. So what does this give us here? Well, something like this in the code. Again, we have this interface here for our sorts. Because this is going to be our base class, we have a virtual destructor, or I should make this virtual. Apologies for that. And we have a sort here, and this is serving as our interface here, lines 4 through 8, because basically that interface means we have to implement this purely virtual function in C++. That's how we do things. In other languages, you might be able to just declare this as an abstract class or actual interface or must implement function. There's various ways to do that. But then of course you can see our derived types here. Insertion sort, which implements isort, so we have to implement this sort function, and same thing for bubble sort. Okay, so now at runtime, if I advance the slide, you can see that I'll create something that is of type sort here, and it's a pointer, the sorting algorithm, and we can just create new insertion sort, or I could do new bubble sort. And then when I run the sort here, I just use runtime polymorphism right here where my cursor is over my shoulder, and it'll call the appropriate sorting algorithm. So in this case, it's of type, if I move out of the way here, insertion sort. So it'll do the insertion sort and call this function and sort the data appropriately. So that's the idea here. Now, of course, if you follow my channel, we should do some modern C++ things. So here's the same exact thing, but just using unique pointers, and this will work just the same here. Okay, so no problems there. So I'll try to use this example. Now, one thing to observe here, I've gone with an object-oriented approach. I've said inheritance is a great tool for this. Now, we have to be a little bit careful with inheritance, so stay tuned for the next few slides, and I'll talk about why. But if you're really anti-object-oriented programming, you could just have free functions or function pointers. That's another way that you could change behavior. And maybe you could even put those into like a variant or something to sort of constrain your set of different functions that you could call, or you could use like an array or something if you wanted as well with the different functions. Again, there's different ways that you could sort of set this up, but consider that the advantage that you get with inheritance is that you have type checking, right? So you make sure that you are selecting something that is a type of isort, and you do have an interface that you have to code to. So oftentimes those might be, important things because you want overall to be able to achieve your goal of sorting or something in that family of algorithms. So you want to make sure that it has all of the capabilities to finish the job at the end of the day, which in this case it's just sorting, but you could imagine something more interesting like a graph traversal where you might have to do multiple steps, or there might be multiple phases that you want to do with that particular algorithm. So just keep that in mind. There are other non-object oriented solutions, as I've mentioned here. But again, inheritance is kind of the appropriate way to approach this strategy pattern here, or what we're building up to. So anyways, now that we've got these building blocks for doing our sort, I would say that this code's becoming a little bit more maintainable. We've built things into these nice building blocks where we have insertion sort, bubble sort, etc. And you can see what I've basically implemented here in this function here, and I just call it generic underscore sort just to have something different. That same sort of functionality that we saw in the C++ library. I say if our collection size is less than 16, then I've just made up do bubble sort. Otherwise, do insertion sort. Okay, so that's the basic idea here. So we've got these individual sorting classes that have just one responsibility. So generally speaking, if we can get our behaviors to doing one responsibility or one sort of behavior, that's good. Sort's kind of natural for that, right? We've got one task, just sort things and give us the data. So that works out nicely. But again, that's something that you might also consider that is just nice object-oriented programming. Okay, so now that we have this idea of using inheritance to group a family of algorithms together, right, the different types of sorts, we can start thinking about, well, are we managing the complexity well? So I've got, this ability to group related things together, but did this manage our complexity well? I will argue to some degree we have, right? We've grouped together our sorting algorithms. This is reasonable. One sort of behavior per class. We have an interface that we can code to. So this is, generally speaking, pretty nice code here. We could nitpick. Maybe there are different performance things, and we'll get to that in the pros and the cons in the next video about adding inheritance, because that does have some overhead. But generally speaking, the complexity is pretty well managed. Someone can look at this and say, oh, you're using bubble sort here. I understand that it's different from insertion sort. Okay, so that's the idea here. Now, of course, again, in managing complexity, we do have to be careful with, maybe we find insertion sort for x86 because there's cool instructions for swizzling or swapping data or something, and we start extending this hierarchy. So there could be some complexity that arises with inheritance. We have to be kind of careful if this hierarchy were to get too big. So maybe you could kind of, try to avoid deep hierarchies, and, maybe we could just point everything to isort. So again, that's just a little note on being responsible with inheritance. So anyways, on the testability of this refactoring, or rather using one object per sort here, this is pretty good. This is pretty easy, right? I can write a unit test and instantiate each of the different sorts and test the behavior. I can even parameterize these unit tests with the different type of sort that I want to do, and have a bunch of different sizes and so on. So again, this is pretty testable. I think it's easier to do test-driven development in this manner of, writing your test first and then the object, and then we know what the assert is going to be. Okay, and again, we could try to do this at compile time as well with static asserts in some cases. So again, this tends to probably lend itself a little bit better for a test-driven development strategy. Okay, writing the test first, and then the object that'll implement that behavior. Okay, so reviewing our goals with that in mind, we went down a little bit of a understanding of how we get to inheritance and how that can be our tool for grouping related families of algorithms together. Overall, it seems like we have a more flexible way to choose algorithms. We're just going to use the language's ability to choose the right type. We've managed the complexity, relatively speaking. We don't just have a bunch of free code or functions hanging around. They're all grouped together and encapsulated. And I'm arguing that there's probably a good use case or a good rationale for making this easier to test. And that exactly matches our idea of the pattern that we're trying to implement today, the strategy pattern. So again, here is the pattern here. Keying in on the main idea is that the strategy pattern is about enabling the selection of an algorithm at runtime or compile time. We could also do it at compile time. But the idea is, instead of implementing the single algorithm directly, the code receives some runtime instruction as to which in a family of algorithms to use. Okay, so let's talk about when are some examples of having the strategy pattern, because this is where we want to identify where to use it. So drawing your attention here, again, if you have different types of sorts, that's kind of obvious, as we've seen here. That could be a great reason. Maybe you have different compression algorithms. You're choosing lossy versus non-lossy types of algorithms to use. Maybe you're exporting different data sets to different text formats. Maybe you have a bunch of different graph traversals, in order, pre-order, level order, etc. Those are all, kind of obvious cases. Some of the stuff that you might study in an algorithms course or see on a website of grouped together algorithms, right? That tends to fit this. When you want to prevent yourself from redeploying software, that's also another reason to have a sort of family of algorithms that you can select from. Because again, maybe you want to have some sort of backup approach, like algorithms that run in case there's an emergency or resources are running low, that you can select from, versus saying, okay, we got to shut the system down and redeploy and upload data that, every user has to download a patch or something, right? So if there are different options that you can select from or configure, again, that's another reason that you might want strategies, right? Maybe you actually only have one sort algorithm because you've identified it as the best algorithm, but you could have a strategy for the sort that logs, the sort that, saves that data somewhere and, is reported to the user, right? So you can have different sort of, strategies built on top of it, or strategies that use other patterns like decorators and stuff built on top of it. Okay. If you want something, to again, just change the behavior. Again, as I mentioned, I think strategy can help make testing easier just in how you've broken the program into smaller parts. That tends to be the case, I found in my experience, by breaking your program into more modular blocks. It makes things a little bit easier to code in. I mean, just as an example, the standard template library in C++, I like having a lot of different building blocks that I can build up an algorithm, right? So that should sort of make the same sense that if you're building programs with complex behavior, if you have little building blocks to build that, they're easier to test and write correct software. And again, where we sort of started this journey on identifying where the strategy pattern is useful, again, maybe if you find yourself with multiple condition statements, a giant switch table, a bunch of go-tos, lots of conditionals, any of these sort of things, that's where you're going to want to use the strategy pattern here. Okay, so let's see if we could try to identify it in the wild. And then as mentioned in the next video, so make sure you stay subscribed, of course, we will implement the strategy pattern from scratch. Again, it's not a crazy or hard pattern to use. In fact, maybe you've identified some places in the C++ standard library where it exists. So pause and think about that for a moment. And if you paused and thought about it for a moment, well, execution policies, for instance, might be one example. Choosing to do something parallel or not parallel. Comparators, anytime you're doing that, you're changing the strategy, maybe of how you're comparing or sorting the data. So that's just with a function, you're changing the strategy. Allocators, right, might be something, and that's sort of at compile time usually, how you're working with memory. So again, these are some different places in the wild here. How about this as an exercise? Well, actually, again, that idea policy-based design comes from this book by Andrei Alexandrescu, Modern C++ Design, which is basically the strategy pattern, usually at compile time is where you're thinking about it. Okay. But how about this? How about this application here? This is the GNU image editor, GIMP. Where's the strategy pattern here? Could you identify anywhere where you might want to switch strategies as you're doing things? And if you thought about this for a moment and pause the video, well, I mean, look all around. Anywhere where you have a tool and you're clicking with your cursor, maybe you're changing the behavior. Maybe it's doing a flood fill versus just a little pencil mark. Or maybe even within the flood fill, you're changing the algorithm from some like scan and fill to some other fancy, parallel version of that. Even your brushes, maybe that's a way that you can have different strategies for, spray can or, just using some of these different patterns here. So a lot of the different tools and so on, or selecting things with layers, moving all the layers. Again, these are things that could probably be toggled out based off of the mouse press. So again, you can think about this in many different ways here. Command line applications, again, pretty much everything you use here, like FFmpeg, which has a bunch of different options to choose from. How you encode or decode, right? What algorithm are you using? So tons of different options. Those would be different strategies, different family of algorithm. Am I outputting this version of MPEG versus using this encoder, etc. Falling Sands game, if you've ever seen these are kind of neat, where you have different particles. So sand, water, fire, mud, acid, salt, all these different elements, metal and so on, and how they interact with each other. That's somewhere where you'd probably have a bunch of if, else if statements for what you're creating or how these particles are interacting with each other. So I thought this was just another nice example of where you'd probably have some family of related elements or particles, however you want to think about this, and how they interact with each other. All right. So anyways, we'll get a little bit more formal with the strategy pattern in the next video, but I'm going to go ahead and end it here. So I hope you enjoyed this lesson. If you did, let's go here. You can go ahead and find, I'm going to put all my software design lessons on my site here, courses.mshell.io. So feel free to check that out so you can follow your progress in a distraction-free environment. Sometimes YouTube can get a little bit distracting. And those will be available, and you can check out any of my other courses as well there. And with that said, folks, let me know if you've used the strategy pattern, if you've heard about it before, if you've thought about interesting use cases where the strategy pattern has been very useful, and if you agree that or disagree with anything in the video about the strategy pattern. I found it to be one of the most useful personally, and I think it's a nice one for programmers to think about as a way when you're organizing your code, especially if you have lots of different behaviors or user-defined behaviors that you want to plug in. So anyways, folks, thanks for your time and attention, and I'll look forward to seeing you in that next video where we'll code up the strategy pattern.